Hello everyone, welcome back to another devlog. I'm finally making some progress on my engine again, so I thought I'd share a quick update on where I'm at with the project. I recently bought a new MacBook to use for work, and I've really been enjoying it so far. The only problem was that my engine wouldn't run on it at all. The issue is that my MacBook reports that it doesn't support hardware ray tracing, which my engine relies on. I was confused at first, since Apple's M4 chip was specifically advertised to support this. But digging deeper, I found that hardware ray tracing is only supported on Metal, Apple's graphics API. Support has not yet made its way into Molten VK, the layer on top of Metal which allows Vulkan apps to work on Mac. Instead of waiting a potentially very long time for macOS hardware ray tracing support on Vulkan, I decided to refactor my engine to work without it. The Vulkan hardware ray tracing pipeline looks like this. The main bit of work that the hardware does for us here is the top-level acceleration structure traversal. This determines which object intersections to compute for each ray. If we want the engine to work without hardware ray tracing, we'll need to write a software-based implementation of this. Probably the most common type of acceleration structure is a bounding volume hierarchy, or BVH. This is what I chose to implement. A BVH is a data structure that hierarchically groups nearby objects together, storing axis-aligned bounding box at each level. Ray bounding box intersection tests are very cheap, so the idea is to check intersection with each node in the BVH recursively, skipping all children of nodes not hit. This lets the ray easily skip checking intersection with large groups of objects at once. Given a group of objects, along with their transforms, we can construct a BVH in a top-down manner. We begin by computing a bounding box containing each object, then taking the union over all boxes to get a bounding box containing the entire scene. Now, we partition the objects into two groups using some heuristic, and compute the bounding box for each group. The algorithm then continues recursively on each partition, further partitioning the objects until some minimum object count or box size is reached. Each node then stores its box size along with references to its children, be those other nodes or the renderable objects. Once a BVH has been constructed, we can use it to compute which objects a given ray is hitting. A ray first performs an AABB intersection test on the top-level node's bounding box. If an intersection is found, the node's children are added to a stack. While the stack is not empty, we will continue popping nodes off and checking for intersections, again adding each node's children if they were hit. By the end, we have a list of all objects the ray hit. With those two core algorithms, we're able to efficiently render multiple voxel volumes in one scene. But how did we determine where to split the objects during BVH construction? There are a lot of potentially good ideas. We could split along the midpoint, or maybe try to keep the number of objects equal in each partition, or any other crazy heuristic you can think of. In practice, most implementations use what's called the surface area heuristic. This is a heuristic that aims to estimate the computational cost of each possible partition. Naturally, the lowest cost split is the one we should take. This heuristic requires that each object have an estimate of how computationally expensive it is to intersect. We call this T-intersection. For voxel volumes, you might estimate this using the size of the volume, for instance. The heuristic also requires the cost of simply visiting a node in the BVH to be estimated. We call this T-traversal. If the node we're processing were to become a leaf node, the total cost incurred would be the sum of T-intersection for all its child objects, since we necessarily need to intersect all children. If we instead decided to split the nodes into two partitions A and B, then the total cost would be the cost of traversing down the node, plus the sums of the object cost in each partition, weighted by the probability that the ray actually hits each partition. The probabilities PA and PB are a function of the partition itself. Larger partitions lead to higher probabilities, as the ray will be more likely to hit it and traverse down the node. As it turns out, the probability that a uniformly random ray passing through a box also passes through a child box is exactly the ratio of their surface areas. So we can directly compute PA and PB by taking the surface area of each candidate partition and dividing them by the total surface area. To compute the best split, then, we simply consider each possible partition, compute its cost, and choose the lowest one. This will help create trees that are optimal for ray tracing. If you want a better explanation of BVHs or anything ray tracing related in general, you should check out the book Physically Based Rendering by Farr, Jacob, and Humphreys. It's freely available online and was super interesting. Now that the BVH traversal is working, all that's left to do is to refactor all of the engine's shaders to use the hardware tracing pipeline only if it's available, and fall back to the software BVH traversal otherwise. This essentially boiled down to a bunch of macros and forking logic in the renderer. The codebase now uses 3 shaders for each job: the common shader with all of the actual logic, and both a hardware and software version which provide any pipeline-specific definitions. And now, the engine finally runs on macOS. In fact, removing the reliance on hardware ray tracing greatly increases the number of GPUs that can run the engine. The hardware ray tracing extensions are only supported by about 10% of all Vulkan-enabled devices, while the rest of the extensions used by the engine are supported by more than half. Before I benchmarked the new BVH implementation for a comparison, I wanted to improve the current demo scene. The old one is pretty flat and already runs at over 60 FPS. Where's the fun in optimizing if the frame rate is locked by VSync anyway? My voxel modeling skills can only take me so far. So I first decided to write a mesh voxelizer so I can use assets made by actual artists. This was pretty straightforward, just involves computing a bunch of triangle AABB intersections. Now, the engine has access to an endless library of assets and full scenes. Then, after stealing some assets from online and tweaking the terrain generation parameters, our scene is looking much nicer. Now for the benchmarking. Here are the render times for the forest scene, along with a few others. Each was rendered at 1080p with hard shadows and GI enabled, which I think is the best looking configuration. I really have my work cut out for me here. The next few months will be dedicated to optimization. I also plan to implement a new GI algorithm, as I'm pretty disappointed by the performance of this one. My GI rays and final gather take embarrassingly long, likely due to bad cache locality. Next devlog, I'll talk more about my approach to improving this. I also plan to add a sort of depth prepass to improve the primary ray timings. Thanks to everyone for sticking around. The next devlog will definitely come a lot sooner than this one did. I'm finally settled into my new job and have been making good time to work on the engine again. I also hope to make a video about my job soon, as I actually get to work on some really cool voxel-related stuff there too. See you then.